called Hot Topics. Okay? We have 5 small talks in this session, and I'll introduce the first speaker. He's Dr. Luca Argenti from University of Central Florida, and he'll be speaking to us about the birth of resonant photoelectric wave packet. So let us welcome Dr. Luca Argenti. Luca.
So, first of all, I would like to thank very much the organizers for giving us the opportunity to present our results here, this beautiful conference in a beautiful city. So, when an atom or a molecule is ionized, you liberate an electron in the continuum. This process is fast, sub-femtosecond time scale, but the system can also be trapped temporarily in a metastable state before it decays. And the time scale for this second process can be on the few femtosecond or tens or hundreds of femtoseconds. So the ionization is inherently a process that entails multiple time scales. During this talk, I will show how attosecond techniques can be used to reproduce, to decode, to analyze the dynamics, the ultrafast dynamics of ionization at all these time scales at the same time. The outline of my talk is as follows. So first, I will go through rapidly the phenomenology of resonance in the energy spectrum and in time domain. And I will go again through some incarnation of the rabbit technique to show how to measure those properties in time. And I will illustrate a couple of recent experiments where we did use the rabbit technique to reconstruct a resonant photoelectron wave packet as it is born in the continuum, and draw some conclusions. So first of all, if you want to measure a photoionization spectrum, you go to a synchrotron and say you set your sample in a vacuum chamber. You illuminate it with the radiation from the synchrotron, which has a very broad band. Some light gets absorbed, the system gets ionized, and you disperse the light on a photographic plate, and this is the result that you see. So you see vertical lines that are corresponding to the excitation of metastable states. This was interpreted long ago by Fano, who argued that there is a parallel process where the system is excited to a doubly excited state, which subsequently decays, and the interferences of these two different alternative paths gives rise to the starkly asymmetric shape of the Fano profile. And the form of this shape is well known. Now, when you do this kind of experiment, however, even if it is infinitely precise, you lose a lot of information. And the reason is that by dispersing the electron, the photoelectron wave packet, you lose all the relative information between the different phases, you lose the information of the relative phase between the different chromatic component of the photoelectron wave packet. So this means that you lose information on the timing of the photoemission. Now, the phase of the transition amplitude is known. And so let's look what we lose in a photoelectron spectroscopy experiment at a synchrotron. The amplitude is proportional to the Fourier transform of the field at any given frequency, omega times a phase factor, where epsilon is a reduced detuning from the resonance, which is complex. Actually, this shape here describes a circle in the complex plane. If you start at very negative detuning, you are close to 1. Then as you approach the resonance, the phase of this amplitude drops drastically by pi as it crosses from the first to the third quadrant, and then progressively it recovers to 0, with giving rise to this sigmoidal shape for the phase. It is this sigmoidal shape that is responsible for the dynamics of the wave packet. How does a wave packet with a resonance look like? Let's see it. So if I illuminate helium near the doubly excited state with a sub-femtosecond XeV pulse, what I get is a density of photoelectrons coming out. And you see there is a big wave front that saturates my color scale, and followed by a tail of photoelectrons that are associated to the decay of a resonance. Now, this structure changes in time because the propagation is dispersive. So eventually, at large times, your wave packet resembles the spectrum itself. But at short time, it doesn't. And this is what we have lost at the synchrotron. And if you look at what has arrived in the continuum at a finite time by truncating the wave packet, what you get is the formation of the Fano profile across time. And this formation starts with a smooth spectrum when the resonant hasn't started to decay, followed by several fringes with an increasing crest and a through that forms until you get to the Fano profile with a 0. And this kind of formation of the Fano profile was suggested approximately 10 years ago by the group of Joachim Burgdorfer. Now, let us see how we can reconstruct that phase with Rabbit. So you have already heard everything about high harmonic generation. So you know that if you illuminate an active medium with a strong IR pulse, you get a sequence of attosecond pulses that give rise to a spectrum of harmonics that are odd multiples of the IR frequency. And the demonstration that actually these harmonics are in phase so to give rise to an attosecond pulse train was done in 2010, where the Rabbit technique was actually introduced. Now, we want to look a little bit deeper in this Rabbit technique. If you shine this attosecond pulse train together with a replica of the IR pulse that was used to create it with a measurable time delay, and you shine it on a target like argon, ionize it, you see lines corresponding to the harmonics, but also you can exchange an additional IR photon, giving rise to sidebands. And for each sideband, there are multiple paths that interfere, giving rise to a beating with a characteristic frequency of 2 omega, plus a dephasing, phase shift, which has 2 components, one which is the intrinsic phase of the 2 harmonics contributing to the sideband, and the other one, which is the phase of the 2-photon transition matrix element to the continuum. This is essentially the coefficient of the photoelectron wave packet in the sideband. It is complex, and if the phase of this matrix element changes with energy, this means that the sideband wave packet has a group delay with respect to the harmonics itself. So it is slightly anticipated or delayed. And indeed, this technique was used to measure the relative time delay between emission from different shells in rare gas atoms. Now, what happens if instead of a smooth continuum, we have also resonance? Well, beyond the ionization path that we have seen so far, you can also do something more. You can excite from the ground state the states that will eventually decay, and these states eventually does decay, emitting in a coherent way, for example, an IR photon, or it can decay in a radiationless process by Auger, and subsequently the continuum electron exchanges an IR photon, or you can excite ardent ion plus an electron in the continuum. These recombine to give the transiently bound state, et cetera, et cetera. All the non-radiative processes here, which are infinite, are summed exactly to infinite order by the Fano model. So if you think of computing the 2-photon transition matrix element using the Fano wave function, you probably get a very good approximation. So we did so, introducing particularly some additional ingredients from the strong field approximation, and you can get a good approximation for the 2-photon matrix element that looks surprisingly similar to the 1-photon transition amplitude for Fano. The only difference is that the Q parameter here is no longer real. It is complex. To test the validity of this model, we compared it with what we think is the best comparison possible. That is the helium atom treated ab initio with the full solution of the time-dependent Schrödinger equation, which is, by today's standards, essentially exact. Here you see the Rabbit spectrum with one of the harmonics resonant with the sp2 plus state. And if you compare the prediction of the model for a time delay 0 as a function of the tuning of the harmonics, ab initio or with the model, a sophisticated version of the model with multiple resonances and folding with the fields, you see that essentially the results are identical. And if you look at the phase shift of the sidebands, upper and lower, as a function of the tuning, and the gray line is the ab initio and the blue line is the model, again, you see that the model works very well. So what we know now is that we have a model that is extremely flexible, extremely accurate, and which we can use instead of solving the TDSC to interpret a gazillion number of experiments, and this is what we are going to do now. So the first experiment was conducted in the group of Van Lullier. It concerns the argon atom, the ionization from the outer 3p shell, in an energy region where the 3s-1 4p state can be excited. This is an auto-ionizing state. So I summarize a little bit what was done. In this case, the light was 800 nanometers, the IR light. One of the harmonics that was resonant with the state was the 17th. So you started with a certain detuning. Absorption and emission of an IR from this resonant harmonic gives rise to resonant sideband signal, which are contrasted with the reference from the upper and lower harmonic, and you get a time delay spectrum for the rabbit. And you can see that there is a phase shift of the upper and lower sideband compared with the reference, which are the farther up sideband or farther down sideband here. So you measure that phase shift as a function of the detuning for multiple detuning, and you get a resonant profile, which is the sigmoidal structure that we have seen at the beginning. So we were happy with that. We managed to see, actually, the phase of the resonant transition. The experiment are the black dots. The theory, our prediction, is the red line. And this was, in a way, a success because it was accepted eventually in Nature Communications, so we are happy. However, there are admittedly still some issues with this experiment and the theory. The first is that in the experiment, you have to repeat a rabbit measurement for each and every detuning. And the second is that in this experiment, what was looked at was the integral signal of a sideband. So the resolution that you have in energy is the width of the harmonics itself. So it is a low resolution. On the side of the theory, we described pretty well the features. We also actually were able to tell to the experimentalists what the blue shift of their harmonics was. We can do so rapidly, but there are still some discrepancies, and that are, we believe, mostly due to the fact that we treated the continuum-continuum radiative coupling in a cavalier way, plane wave approximation, which sometimes works, sometimes doesn't. And the other is that we neglected the spin-orbit splitting of the parentine. But the work on this is in progress. The second experiment that overcomes most of the limitation of the first is done in helium. It is similar to the first, but it differs from it in two substantial ways. The first is that, well, it is conducted with a 1,300 nanometer red light, well, infrared light. And the infrared light itself, the pulse, is no longer 15, 20 femtoseconds, it is 70 femtoseconds. However, the XUV harmonics are still pretty large. They are corresponding to a duration of an harmonics of the order of 6, 7 femtoseconds. So this is the first thing. Now, the energy resolution of the IR is way, way better than before. The second thing is that instead of measuring the integral signal of the sideband, now we resolve it in energy. And now, what does that mean? It means that instead of having to repeat many, many experiments with different detuning, now in just one shot, we measure a dozen different detuning at the same time. It is just sufficient to look inside the sideband different energies, because a portion of the sideband just receives contribution from the corresponding portion in the upper harmonic and in the lower harmonic, just because the IR is so monochromatic. And if we compare the structure, the inter-sideband structure of one beating, we see that our model reproduces pretty well the experiment. So you see this duckling shape, where you have essentially an amplitude with a slowly varying phase. At a certain point, well, let's look here. At a certain point, the amplitude vanishes, and the phase shifts dramatically, and then rapidly returns at the value of before. So this is the sigmoidal structure that we saw before. And if you plot it, actually, you can see that the excursion in the phase extracted with this method is 2 or 3 times bigger than what would have been obtained if we have used the integral formulation instead, conducting several rabbit experiments with different detuning. So there is a great gain in the resolution of the phase. There is overall a very good agreement in the amplitude that is recovered from the experiment compared to the amplitude in our model, where everything is perfect Gaussian pulses. But the agreement is not perfect because in the experiment they do not have perfect Gaussian pulses. However, the agreement of the phase where the pulse, where the sideband signal is different from 0 is very good and is actually very robust. We recover the same phase structure no matter what the tuning is. So we are very happy with that. And now we do have, for the sideband, the amplitude, the phase, and we can do an inverse Fourier transform and reconstruct the wave packet itself. So here you see the magenta line. It is this double peak structure with this small tail here, and it is fully reconstructed from the experiment with just an inverse Fourier transform and no input from theory whatsoever. And the interpretation is similar to what we have seen in the TDSC simulation before. You have the direct ionization peak here, followed by a minimum that is due to the interference, destructive interference between the direct ionization and the resonant tail. Then you have a resonant tail here with this bump that we don't know where it comes from, actually. It is probably due to the shape of the pulse itself. And a decay that is actually faster than expected. So if we look at the theoretical wave packet, it is the red light, so the red line. So this is literally the wave packet, analytical wave packet. The light blue line is what we would reconstruct if you used for the reconstruction, not the experimental spectrum, but the theoretical rabbit spectrum. So the reconstruction principle works perfectly well. And the blue line, the dark blue line, is what we get if we reconstruct from the theoretical spectrum the wave packet after having convoluted it with the resolution of the electron spectrometer. So it is the electron spectrometer that kills the exponential decay and makes it a Gaussian decay. And you see that at large time it matches perfectly well what is reconstructed in the experiment. Since we have the wave packet with amplitude and phase, one may also want to truncate it at finite times and see what the spectrum of the electron emitted so far looks like. And indeed, if you do so, you see that first the spectrum is symmetric, and then a through starts to appear, and the peak splits in two parts. So this would be the Fano profile. And this is a reasonable reconstruction of what was predicted by Marlene Wickenhauser in the group of Joachim Burdorfer 10 years ago. So in summary, we have shown that attosecond two-photon interferometric spectroscopy is able to provide phase information without necessarily using theoretical input. We showed that rainbow rabbit, that is energy-resolved sideband spectroscopy of a rabbit spectrum, gives the phase information with less effort and with unprecedented resolution. And when you combine that with theoretical predictions, it is possible also to infer properties of the photoelectron wave packet. And with this, I would like to mention all the people that were involved in this. Two big groups, experimental group of Anne Lullier in Lund, the group of Pascal Salière in Paris, the theoretical group of Eva Lindroth, of Alfred Maquet, and of course, most of the results that you have seen for the theoretical part have been computed by me with my previous group leader, Fernando Martin in Madrid, by Álvaro Jiménez Galán, who is now a postdoc in the group of Olga Smirnova and Misha Ivanov. And I would also like to take the opportunity of this talk to highlight my newly formed group in Orlando, Florida. And I thank you for your attention.
Nice talk. I stood a little bit early, actually, but we have plenty of time for discussion. So, is there any question or comments? Let me ask the first question, actually, though. So you measure the time evolution of your wave packet, right? But what about the spatial part you consider is already known?
If I consider what?
Spatial part of this wave packet, do you consider that is already known or you don't need to?
So this is actually a very good question. So the reconstruction of the wave packet is made under the assumption that you are reconstructing it as a function of time at a fixed distance from the atom, let's say 2 atomic units. And under the assumption that it is essentially a plane wave. The subsequent distortion of the wave packet is not taken into account. So it is not illustrated here. So it is the wave packet in time, and we haven't elaborated on that. And if we did, we would assume that it is formed by Coulomb waves. So it would be, in a way, trivial, the evolution. If there is a non-trivial evolution due to interchannel mixing in other systems, not helium below the n equal 2 threshold, then it would be an interesting issue to address. Say above the n equal 2 threshold, as it was discussed by previous speakers, then yes, there is also an issue related to the time, the spatial evolution, yes.
Or, thank you very much. For other questions, do you have? Comment? There? No? Let me ask you another question because we have some time, right?
Okay.
So do you consider rabbit? In the previous talks also, they also consider rabbit. Do you have an alternative method? Because rabbit actually has a repetitive patterns. Sometimes I found this quite difficult to understand, interpret, but do you have other methods to study the same thing?
Other method to do so? So actually the streaking is an equivalent method to the rabbit as long as you do it with weak light. So essentially in rabbit you have XUV plus IR, and they interfere. In the streaking you have the same thing, XUV plus IR, which however interfere with the XUV itself, and gives rise, instead of changing intensity, you gives rise to change in direction, in the asymmetry with which the photoelectron is ejected. So in the weak field limit, they are essentially equivalent, and the streaking would be a way to measure the things. Actually, there are measurements now done in argon for the streaking in the presence of resonances, but they are not fully analyzed. In that case, not using a field that is strong enough is difficult because you lose resolution. However, allow me to say that in this case, you are not constrained to narrow signals. In the specific case of the rainbow rabbit, the width of the harmonics is pretty large. It's much larger than the width, natural width of the resonance. So you can cover the whole resonance with just one harmonics. You can cover the whole continuum with just 3 different measurements. So you can map the continuum of the variation of the phase in the continuum for the whole system with just 3 rabbit traces. And that is true for that atom, but also for any other system in principle. And also allow me maybe to mention that the model that we have discussed for the resonant transition may also be applicable to the case of surface states, in the case they were coupled to a conduction band and also to photoemission. So in that case, it would be similar to the problem of argon that I have discussed. And the same phenomenology should be visible there as well. So probably all these techniques have a wider applicability than just gas phase atoms.
Okay, thank you very much, Dr. Argenti.
Thanks.
So let us thank the speaker again. Okay, now we'll move on to the next talk. Next talk will be Dr. Andy Kung from Institute of Atomic Molecular Science, Academia Sinica in Taiwan. He would talk about multi-plate supercontinuum generation, new approach to single cycle pulses and isolated attosecond pulses.